Today we are going to discuss few special cases in simplex applications. We have already done different approaches for solving linear programming problem using big M method, two-phase method, normal simplex method. Today we will talk about the special cases. Number 1 we will discuss, that is the alternate optimal solution, or in other sense infinite number of optimal solutions. If you see, this is number 1. Number 2 we will discuss about unbounded solution. Number 3 we will discuss about the degeneracy cases and the cycling, when cycling occurs and the degeneracy occurs, and infeasible solutions. Although infeasible solutions we have already discussed, just maybe by one example we will show it. If you note, in the simplex table we are having Z j minus C j. Whenever Z j minus C j is greater than equals 0, we say that the optimum has attained, optimum has achieved. Now, whenever Z j minus C j is equals to 0 for basic variables, this is equals to 0 for basic variables, and Z j minus C j is strictly greater than 0 for non-basic variables, in that case we say that the solution is optimal BFS, whatever we have obtained, that is unique one. Now, if this condition is not satisfied, that although Z j minus C j is greater than equals 0 and Z j minus C j is 0 for basic variables and Z j minus C j, not all Z j minus C j is greater than 0 for non-basic variables, we want to check that particular point. So, let us come to the first one, that is alternate optimal solution. Or we may say that infinite number of optimal solution. We will explain it with the help of one example. Let us take the problem, maximize Z equals x 1 plus 2 x 2 plus 3 x 3 subject to x 1 plus 2 x 2 plus 3 x 3 less than equals 10, x 1 plus x 2 less than equals 5, x 1 less than equals 1, and x 1, x 2, x 3 is greater than equals 0. Please note one thing, that here in this particular example, what happens, one of the constraint is parallel to the objective function. We will discuss this after some time. First, let us come to the write down the standard form of the LPP, so that we can form the simplex table. So, the standard form of this table is maximize Z equals x 1 plus 2 x 2 plus 3 x 3, and we have to, since 3 less than equals inequalities are there, we have to introduce 3 slack variables. So, we are writing 0 into x 4 plus 0 into x 5 plus 0 into x 6, subject to x 1 plus twice x 2 plus thrice x 3 plus x 4, this is equals 10, x 1 plus x 2 plus x 5, this is equals 5, and x 1 plus x 6, this is equals 1, x j is greater than equals 0, where j is 1 to 6. Already we have done the standard form of this one. So, in the standard form, once we are writing in this particular format, by incorporating the slack variables for 3 less than equals inequality constants, we are getting the standard form. Now, let us form the first simplex table. The first simplex table we are just writing like this way. you see the this one. So, your Cj is here A1, A2, A3, A4 these vectors. So, it is 1, 2, 3, 0, 0 and 0. You can get it from this one 1, 2, 3, 0, 0 and 0. Your obviously one thing I forgot to tell you, that is your basis is, that is vectors, basis vectors will be x 4, x 5 and x 6, because they are forming the identity matrix over here. So, the basis vectors will be, in this case it is A 4, A 5, A 4, A 5 and A 6, whereas this will be x 4, x 5 and x 6. So, value of C b is corresponding to A 4, A 5, A 6, C j is 0. So, C b is 0, 0, 0. Now, B values are 10, 5 and 1. So, from this one, from this table if you see, it is 10, 5 and 1. So, we will write here 10, 5 and 1. Now, the next first constraint we are writing, that is 1, 2, 3, 1, 0 and 0. 1, 2, 3, 1, the coefficients of x 5 and x 6 are 0. Similarly, for the next one it will be, for x 1 coefficient is 1, for x 2 the coefficient is 2 and for x 5 the coefficient is 1. All other coefficients are not there. So, they will be 0. And for the third constraint, this is you are having only x 1 and x 6. So, the coefficients corresponding to x 1 and x 6 is 1, whereas for all others, that is A 2 to A 5 it is 0. So, we are writing this. So, from the standard form of the table, from the standard form of the problem, we are first drawing the initial simplex table. Now, we will calculate the z j minus C j value. Z j minus C j means C b into A j, means this into this, 0 into 1 plus 0 into 1 plus 0 into 1. So, 0 minus C j, C j is minus 1. On the same way, this values will be 0 minus 2. So, it is minus 2, this is minus 3. Here in this case for A 4, 0 into 1 plus 0 into 0 plus 0 into 0 minus 0. So, this is 0. Similarly, for A 5 and for A 6 also it will be 0. So, the most negative one is this, therefore, A 3 is the entering vector. Now, we have to calculate the ratio x b r by y r j. Your x b r is b by A 4, that is sorry b by A 3 column. So, first one is 10 by 3. The next one if you see 5 by 0. So, this is cannot be counted, because we will take only the greater than 0 cases, positive values only. The next one also will be 0. So, it is also negative. Therefore, the outgoing vector is this one. One thing I forgot to tell you, just see this problem. For this problem, what I want to find out the 4 alternative optimal solutions. We want to find out for this problem 4 alternative optimum solution. Okay. So, it is not that obvious from the problem itself that there is no unique solution. We will see it whether there is unique solution exist or not. So, once I am getting this one, so pivot element or key element is this thing. So, we are obtaining this C j again will remain same 1, 2, 3, 0, 0, 0. So, now the vectors in the basis will become A 3 is A 3 sorry x 4 is going out and x 3 is coming. So, it will be A 3, A 5 and A 6. So, that here it is x 3, x 5 and x 6. So, the values will be corresponding values from here we can get 3, 0 and 0. Once we are obtaining 3, 0 and 0. So, now what I have to do? I have to make this element as 1 and these two corresponding to this row, the next two elements should be 0 in the column entering vector column, already it is 0. So, I do not have to do anything, only thing I have to divide it by 3 to make that key element as 1. So, 10 by 3, 1 by 3, 2 by 3, 1, 1/3, 0 and 0. The next two from here we are dividing by 3, so that it will be 1 and we got this particular row. For the next two rows, if you see already 0 is there. So, there will be no change in this. So, it will be 5 1 1 0 0 1 0 and the next one is 10 by 3, this will be 1 1 0 0 0 0 and 1. So, in the next iteration we are getting this table, again we have to calculate the Zj minus Cj value. Your Zj minus Cj value, again if you calculate, this is 3 into 1/3, that means 1, these two will be 0. So, 1 minus 1, it is becoming 0. The next one is 3 into 2/3, that is 2, next two elements will be 0. So, 2 minus 2 again 0. For the third one, if you see 3 minus 3, 3, these two elements are 0. So, it will be 0. Next one is 3 into 1/3 1. So, it is 1 and the next one will be 0 and 0. So, what we are observing from here, you see we got the optimal point. Here Zj minus Cj is greater than equals 0 for all j. Zj minus Cj is greater than equals 0 for all j. But note one thing in this case, that Zj minus Cj is not all Zj minus Cj is greater than, strictly greater than 0 for non-basic variables. Here basic variables are A3, A5 and A6, non-basic variables are A1, A2 and the other one A4 is greater than 0, but the non-basic variables A1 and A2 is equals to 0 and equals to 0, they are not greater than 0. Therefore, you will not obtain, as per theory, you will not obtain the unique solution, but in this case you will obtain infinite number of solutions. You will obtain infinite number of solutions for this case. Since this is the optimal table, Zj minus Cj is greater than equals 0. So, one optimal solution you can always write down as one solution your will be x 1 equals 0, because x 1 x 2 is not there. So, x 1 equals 0, x 2 equals 0 and x 3 is 10 by 3. From the last table itself, it is clear, x 3 is 10 by 3 and x 1 x 2 is not present in the basis. Therefore, x 1 x 2 will be equals to 0 and x 3 equals 10 by 3. And if you calculate the value of the z max, then value of the z max will become 10. Now, if you see from this table, so this is one optimum solution. I will write down this. This is your one optimum solution. From the last optimum table, if you observe one point, that value of Zj minus Cj are 0 for the non-basic vectors A1 and A2. For the non-basic vectors A1 and A2, Zj minus Cj is equals to 0. Thus, from this table we can make two different tables by incorporating, by entering once in one table A1 as a basis vector and another one in another table A2 as a basis vectors, by excluding any one of these two x 5 and x 6. Since the value of corresponding to Zj minus Cj for these two values are 0, therefore, if you enter any one of these two, the cost function will remain unchanged. It will not increase since the value is 0. But if you take x 4 or A4 column, here if you find Zj minus Cj is 1. So, if I try to enter the value of A4, then the value will be changing. For this reason, from this table we can form another table by incorporating first a 1 as the entering vector. That means, now you will have a 3, a 1 and a 6. These are the, if you see from here, this is your table, your a 3, a 1 and a 6 is coming. So, we are replacing a 5 by a 1, and the reason is that the value of z j for corresponding to vector a 1 is 0. So, if we change the value, if we enter a 1 and the basic, then there will be no change in the cost function, and all other things will remain same. This will be 1, 2, 3, 1, 2 and 3. Your C B is now, in this case a 3 is 3, x 1 we have entered. So, 3, 1 and 0. So, if you calculate now these values, you will obtain this corresponding to a 1 row, it will remain same. This is x 3, x 1, x 6. This one, that is second row which was going out, here it is x 5 is going out and it is 1. So, therefore, we are not making any changes. I am just directly write down for this case the values, because the calculation is similar. This will be this row, the other rows will become 5 by 3, 0, 1 by 3, 1, 1/3, minus 1/3 and 0. This is by simple subtraction and multiplication you will obtain it, as we have done it earlier. For the case of x 6, it will be minus 4, 0, minus 1, 0, 0, minus 1 and 1. So, we obtained one optimum solution from this, but since z j minus c j is not equals 0 for the non-basic, not greater than 0 for non-basic variables a 1 and a 2. Therefore, we will obtain infinite number of solutions. Since for the vector a 1 and a 2 both are value of z j minus c j is 0. Therefore, I can take a 1 as the entering vector in the last optimal table, and in the next table I can take a 2 as the entering vector, and I can obtain the other solution. Let us see calculate the z j minus c j value now. Z j minus c j value if you calculate, then again it becomes 0, 0, 0, 1, 0, 0. So, again z j minus c j is greater than equals 0 for all j. So, you will get another optimum solution from here. What will be the solution? X 1 is 5, x 2 is not there. So, x 2 0 and x 3 is 5 by 3. So, let me write down here. Another solution is x 1 is 5. From this table only we are getting x 1 is 5, x 2 is not there. So, x 2 0 and x 3 is 5 by 3. So, x 1 5, x 2 0 and x 3 equals your 5 by 3. If you calculate z max, again you will see that the value is 10. Since we entered a non-basic variable whose z j minus c j value is 0, therefore, the z value will not change, you will only get some other optimum value. So, this is the second solution you can obtain. Now, the way we have done it, next we can form another table, that is your, I can include instead of a 1 a 2 as the entering vector, I can find out another solution, that is another approach. If you see, this is already you have obtained two solutions, this is say x 1 bar, this is x 2 bar equals this. So, since x 1 bar and x 2 bar are two optimum solutions, if you take any convex combination of x 1 bar and x 2 bar, then that one also will be optimum solution. Or in other sense, I can tell that lambda I x I plus 1 minus lambda I into x 1 bar plus 1 minus lambda I into x 2 bar, where lambda I take any value between 0 to 1 is another solution. So, any convex combination of these two for different values of lambda, you will obtain another solution over there. So, if you take lambda 1 equals say half Then using that formula you can tell x 3 bar, that is it will be x 1 x 3 bar, value of x 1 will be equals to 5 by 2, that is lambda into x 1 plus 1 minus lambda into this, like this way if you do it using the formula lambda 1 x 1 bar plus 1 minus lambda 1 x 2 bar, x 1 will be 5 by 2, x 2 will be 0 and x 3 will become 5 by 2. This will be also another optimal solution. If you calculate Z max, the value becomes 10. Let us take any other value, say lambda 1 equals 3 by 4. In that case, you will obtain the fourth solution x 4 in this form, x 1 equals 5 by 4, x 2 equals 0 and x 3 equals 35 by 12. And if I calculate Z max, again Z max will remain 10. So, you are obtaining, this is one optimal solution, this is another optimal solution. So, as we have shown here, you are obtaining 4 optimum solutions. Like this way, any convex combination you take, anything you take, that will be any value of lambda between 0 to 1, you will obtain another optimal solution. Therefore, you are getting the infinite number of solutions for this case. So, please note one thing, in the optimum table whenever Z j minus C j is greater than equals 0 and if Z j minus C j is not greater than 0 for at least one non-basic variable, we will obtain the infinite number of solution. So, this is the first case of our special cases. The next one is the unbounded solution. Unbounded solution. Again, we will explain it by one example itself. Minimize z equals 3x minus 2y, subject to x minus y less than equals 1 and 3x minus 2y less than equals 6xy greater than equals 0. So, we want to show that this particular LP problem admits unbounded solution and we want to check graphically also what it represents, how, that is the reason actually we have taken a function of 2 variables only. Again in standard form, let us write down the function, it was a minimization problem, minus 3x plus 2y, 2 slack variables you have to incorporate. So, w subject to x minus y plus z equals 1, 3x minus 2y plus w equals 6 and x, y, z and w is greater than equals 0. So, in the initial simplex table your basic variables will be z and w. So, that this is forming the identity matrix. So, let us see this one, your this is b value is, then I am writing a 3 and a 4, here it is coming as z and w. Your C j is minus 3, 2, 0 and 0. Therefore, C b will be 0 and 0. Your b value is 1 and 6. Now, you write down the rows, x coefficient 1, y coefficient minus 1, z coefficient 1, w coefficient 0. For the next constant, it will be 3, minus 2, 0 and 1. So, we are forming the table from here. Once we have formed the initial table, we have to calculate the z j minus C j, and z j minus C j will be 0 into 1 plus 0 into 3 minus 3. So, it will be minus 3 0 into 1 plus 0 into 3 minus of 3. So, that you are obtaining here plus 3. Next one is 0 into minus 1, 0 into minus 2 minus 2. So, it will be minus 2 and these 2 will be 0. So, your entering vector is becoming y. So, let us calculate what would be the ratio Whenever you are going to calculate the ratio, please see b by y value 1 by minus 1, it is a negative value, we cannot take. For the second row itself, again b is 6 by minus 2, again it is a minus. So, you cannot take because ratio has to be positive. So, what is happening in this case? You see the entering vector a 2 or this y, this is the most negative. So, it should enter, but can you enter this vector a 2? We cannot enter this vector a 2 because in the ratio we are finding that there is no positive value. What is the meaning? What we will do? The meaning is that if you see your function is, you want to optimize the function, minimize the function z equals 3x minus 2y. So, if you go on increasing the value of y, your optimum value of z star will also, or z will also go on increasing. Or in other sense, you can tell that z equals 3x minus 2y, this will decreases to minus infinity as y approaches plus infinity. Is it clear? So, you are not getting any solution, and therefore, the problem admits the unbounded solution. The reason we are telling it admits unbounded solution. Number 1, if you see the table from here, you are entering, your entering vector is y, but whenever you are trying to calculate the ratio, you are finding that the ratio is negative, means there is no positive ratio. So, no vector can enter into the basis, although no vector will depart from the basis, you cannot depart it. And the reason here also clear, I think from this, the objective function is z equals 3x minus 2y. If you go on increasing y, that is whenever y will approach plus infinity, this z value will decrease to minus infinity. Therefore, there will be optimum solution, there will be unbounded solution for this case. Now, let us see the, for this particular problem itself, let us see graphically what happens. If you see this one, I can write down the, this rewrite the constraints x minus y equals 1 and x by 2 minus y by 3, this is equals 1. If you try to draw the graph of this, you will find this one, this is your 1 0 point. So, this will be 0, just roughly I am drawing. So, one curve is something like this, this is your x minus y equals 1, there will be another one, that is this is x by 2 y by 3. So, this is 2 0, and here you are having somewhere here, somewhere in this case you will have 0 minus 3. So, if you draw, then this is the curve, this one, and so it is going something like this. So, this equation is 3x minus 2y, this is equals 6. So, what is the feasible region in this case? Feasible region is only this portion, it is going on increasing, if you see. So, from the graph itself, it is clear that the solution is, if you see this one, the solution is unbounded, you take any value, it will go on decreasing. If you see the draw the curve, isocost curve, that is the z line, it will be something like this. This is your z equals 3x minus 2y. If you see the reason, the objective function is parallel to the one of the constraint basically here, and the constraints are unbounded. So, from the figure itself also, graphically also, we can say that this is unbounded solution. So, this is the second special case. The third special case is degeneracy. Usually, we say that the degeneracy occurs whenever one or more constraints are redundant. Whenever one or more constraints are redundant, then we say that the degeneracy will occur. We will see how it is redundant whenever we are going to the example. Usually, if you see The degenerate basic solutions are the basic solutions for which one or more basic variables are at 0 level. One or more basic variables at 0 level means I want to say corresponding to this value, what is the value of this? This is a basic variable z, this is a basic variable w. If corresponding b value instead of 1, if it is 0 say, corresponding basic variable is 0, then we say that there exists the degeneracy. How degeneracy will affect us? Degeneracy basically, if degeneracy exists, in that case we say that there is no, it does not ensure that there will be an improvement in the value of the objective function in the subsequent iterations of the simplex algorithm. So, degeneracy, whenever there is exists degeneracy, in that case there is no guarantee, there is no assurance that the function will be, the objective function will be improving over the iterations. So, somehow we can show it by this way. In a particular problem, suppose your a k is the entering vector. Suppose we are considering a problem, obviously we are considering a solution of the maximization type of problem, simplex problem, which is degenerate. That is, we have a basic feasible solution where at least one basic variable value or b value is 0, that we are assuming. On that problem, suppose a k is the entering vector, that is z j minus c j is most negative for this column a k. Now, new value, the z value actually can be written as z old minus x b r by y r k, the ratio into z k minus c k. This is the value. We are assuming that y r k is greater than 0, otherwise there will be no departed variable. So, this assumption has to be there, y r k is greater than 0, and also we are assuming x b r is equals to 0. This we have assumed because the problem generates the degenerate solution. So, x b r equals to 0, that is due to degeneracy cases, this is equals to 0. So, if x b r equals to 0, it has to be for degenerate case, then this part is going to be 0 and the new value of z and the old value of z are same, there is no change, no improvement in the objective function. That is the reason we have told that if the degeneracy exists, there is no assurance that the z value will improve over the iterations. So, basically what is happening, you see, we are starting with a basis degenerate basis b. Suppose there is a degenerate basis b in some iteration. Now, you are going on doing iterations, after n iterations, whenever if you see after n iterations you are coming back to the same basis b. You are coming back to the same basis b, that is, once you are doing n iterations, you are coming back to the old table, old basis. This particular repetition of the tables we call it as the cycling factor. That is, the tables are repeated itself. We are starting from a basis and after n iterations we are coming back, going back to the next basis on the same basis with no improvement of the objective function. This repetition is known as cycling. So, whenever there is degeneracy, there may have cycles. So, we have to deal degeneracy, so that we can obtain the optimum basic feasible solutions. Various methods are available for finding the degeneracy or solving the degenerate problems. Chance problem, chance method, perturbation method, Wolf method, like this way various methods are available. We will discuss only the chance method. Now, what type of situations can occur in degeneracy? Number 1 is degeneracy at initial level. So, you have formed the initial table. In the initial table, you are finding that value of the one of the basic variable is equals to 0. As we have told, the degeneracy occurs whenever in the basis at least one or more basic variable value is at 0 level. So, this is the first case. If you find it, you do not have to do anything to obtain the optimal solution, proceed as usual as we have done for the simplex algorithm, and you will obtain the optimal solution. So, although at the initial stage you are finding that one of the basic variable is equals to 0, you do not have to bother, just go on doing the iterations, you will obtain the optimal solution. But next will come degeneracy at a subsequent iteration, at a subsequent iteration. Now, it may happen that corresponding to key element you are calculating the with the most negative value of z j minus c j is the entering vector. Corresponding to the entering vector you are finding out the ratio x b r by y r j. Suppose whenever you are calculating the ratio you are finding that in more than one row you have the same value, say it is 1, 1, 5 something like this. So, now this particular situation we call it as a degenerate situation. Here if you see, I have to decide whether I should take this depart this row or I should depart this row. I have to be cautious because I am just stating one theorem, that is one theorem is there. When there is a tie in selecting a departing vector, this is the case, when there is a tie in selecting the departing vector, the next solution is bound to be degenerate. So, please note the theorem, when there is a tie in selecting a departing vector, the next solution is bound to be degenerate. Therefore, I have to find out some mechanism by which I can avoid the degeneracy case in the next iteration. I think I have not written the theorem, again I am just stating it. When there is a tie in selecting the departing vector, always the next solution is bound to be degenerate. So, whenever there is a tie, how to break the tie? That means, which one should be the departing vector. So, we will use the various methods are available. I will use only one, chance perturbation method. When there is a tie, what you do? Rename the column vectors of A, rename the column vectors of A. I am just writing in such a way that initial basis B consists of first m column vectors A j of A, or in other sense I want to say, if you take this table, suppose in this table there is a tie in first two rows, then you change this A 1, A 2, A 3, that is A 1 will be equals to new value, old value of whatever basis is there. That means, this A vector will be replaced by these B vectors. In B, how many are there, depending upon that you will take from here, how many vectors or elements of A vector you will take. So, this is the first step. Once you have done this one, I know what is the entering vector. So, suppose A k is the entering vector. So, you are computing, you compute now minimum of this one y I 1 by y I k, y I k is greater than 0 for all I means the rows. So, basically if you see, let me take just one example. Suppose these two are the same. So, in that case basically this value is y I k. if this is the entering vector, y I k will be this value and this y I 1 will be whatever you have changed, that is a 1 equals old a 3 means you will take the old a 3 value. This again will be clear whenever I am going through the one example. So, suppose the minimum occurs at I equals s, in that case we will tell that a s is the departing vector. So, please note this thing that whenever you are telling you are finding the minimum of this, if the minimum occurs for I equals s, the departing vector will be a s. Next, what can happen? You are finding the minimum, but again this minimum value are same, that is again tie occurs. If the minimum value is same, then on this minimum if it is same tie occurs, then what we will do? Number 3, you go to the next stage, minimum of y I 2 by y I k, that is the next. This value index is being changed for all I. Again you whatever minimum value is there, if it occurs at I equals t, then a t will be the departing vector. Again if it becomes tie, then I am writing the general one, that is minimum of y I l, you go on doing like this by y I k, and y I k always should be greater than 0, where your L is equals to 3, 4 like this way n. So, at any of the subsequent iteration you will obtain one departing vector or a minimum I say for equals u, in that case a u will be the departing vector. So, please note this thing that for breaking the tie we are finding using the formula minimum of y I l by y I k. Let us see the first type of degeneracy, that is on the initial basis itself. I have the basis vector is 0. Let us take one example. Maximize z equals 3 x 1 plus 9 x 2 plus x 3 subject to x 1 plus 2 x 3 x 1 plus 2 x 2 equals 0 and 2 x 2 plus x 3 this is equals 1. So, this is already in the standard form, because with x 1 and x 3 we can form one basis. So, the basic variables in this case will be x 1 and x 3. So, it is a 1 a 3 x 1 x 3. I think I do not have to explain now. C j values will be 3, 9 and 1. C b values 3 and 1. So, you copy the values, it is 0 and 1, it is 1 to 0, next one is 0 to 1. So, if you calculate the z j minus c j value, you will find that it is becoming 0, minus 1 and 0. So, therefore, entering vector is this one. If you note this thing, entering vector is a 2, but in the basis one vector a 1, the value of b value is 0. Therefore, it is degenerate problem, because in this table one of the basis variable is equals to 0. Let us see what happens. Let us calculate the ratio. Whenever you are calculating the ratio, this is 0 by 2, 0, this is 1 by 2. So, this is the outgoing vector. So, a 1 will be going out and a 2 will enter. So, on this table you can say a 2 will be there and a 3 will be there. Your pivot element is obviously 2. So, I have to make this as 1 and this column as 0. I am not telling these things, because this is now routine, already you are doing. It is 9 and 1. So, this value is x 2 x 3. You will obtain, I am just directly write down, you can just check whether it is okay or not afterwards. 1 minus 1 0 and 1. Once you are getting this, the z j minus c j value, if you calculate, it will be half 0 and 0. And if you see, your z j minus c j is greater than equals 0 for all j, and also for the non-basic variable a 1, here your non-basic variable is a 1, z j minus c j is greater than 0. Therefore, you are obtaining the optimum solution, unique optimum solution. The solution will be x 1 is not there. So, x 1 0, x 2 is 0, x 3 is 1 and z max, if you calculate, your z max will be equals to 1. So, although the problem is a degenerate problem, but you are obtaining the optimum solution. So, this is the case number 1, when in the initial table in the basis vector, in the basis, the value of the basic variable corresponding to b value is at the 0 level. This is type 1. Let us see type 2, that is whenever there is a tie. Let us consider this problem, maximize z equals 5 x 1 plus 3 x 2, subject to x 1 plus x 2 less than equals 2, 5 x 1 plus 2 x 2 less than equals 10 and 3 x 1 plus 8 x 2 less than equals 12. Obviously, x 1 and x 2 is greater than equals 0. So, since 3 less than equals inequality is there, I have to introduce 3 slack variables and we are writing it in the standard form like this. Maximize z equals 5 x 1 plus 3 x 2 plus 0 into x 3 plus 0 into x 4 plus 0 into x 5, subject to x 1 plus x 2 plus x 3, this is equals 2, 5 x 1 plus 2 x 2 plus x 4, this is equals 10 and 3 x 1 plus 8 x 2 plus x 5, this is equals 12 and x j greater than equals 0, j is 1 to 5. In standard form, we are writing this thing. So, whenever from there we can form the initial table. Now, initial table is very clear. Here from here x 3, x 4 and x 5 will be in the basis. So, it will be a 3, a 4 and a 3, a 4 and a 5. So, this is x 3, x 4 and x 5. Your C j values are 5, 3 is in the coefficient. So, it is 0, 0, 0. C b values corresponding to this is 0. Your b values are 2, 10 and 12. So, you are writing 2, 10 and 12. You are writing the rows 2, 1, 1, sorry, this will be 1, 1, 1, this will be 0, 2. Next one will be 5, 2, 0, 1, 0, 3, 8, 0, 0 and 1. If you calculate z j minus c j value, this is becoming minus 5, this will be all 0, minus 3 and rest 3 will be zeros. So, entering vector is this a 1. Calculate the ratio, the first row 2 by 1 2, for the second one 10 by 5 2, for the third one it is 2. Now, you see there is a tie over there. There is a tie in this case, that is x 3 and x 4 can enter. So, since there is a tie, what I have to do in this case, I have to write down your basically your a 1 from this table itself. If I keep it here, I think it is visible now. A 1 equals, it should be old, a 1 is old, a 3 from the b value, a 2 is old, a 4 and your a 3 is old, a 5. On the same way, these two will be required. So, a 1 is old, a 3, a 2 is old, a 4 and a 3 will be old, a 5. Once you are taking this, now you have to calculate what is the minimum. So, what I will calculate? I have to calculate minimum of y 1 1 by something will come y 2 1 by this. Y 1 1 by corresponding to this, what is there, that only I have to find out. That is corresponding y 1 1 by the first row, for the first row, because it is 1, this value is 1. So, in the denominator 1 will come. Then for the second row corresponding to a 1, the value is 5. So, this is 1 by 5. What will be your a 1 1? A 1 1 will be actually the element corresponding to the vector a 1. What is a 1? A 1 is old a 3 we have told. For old a 3, so y 1 1 will be value of y corresponding to a 3. So, it is 1. So, it will be basically minimum of this one, and y 2 1 this is 0. So, this is 0 by 5. So, therefore, the minimum is 0, that is this one, this occurs for the second one, that is the departing vector will be a 2, or the a 2 is what? A 2 is old a 4 if you see. Therefore, your departing vector will be this one. So, like this way you have to break the tie. I think it is clear. Minimum of y 1 by 1, 1 is coming from here, by 5 for the second one is this one, and what is y 1 1? Y 1 1 is corresponding to a 1. A 1 is what? Old a 3. So, take the coefficients for old a 3. So, 1 and 0 has been taken. So, this is the departing vector. Like this way you have to break the degeneracy. So, once I have done this, let us see what happens to the next one. Therefore, it will be a 3, a 4 will be departing, a 1 is entering, a 5. So, x 3, x 1 and x 5 will come. Your C j is 5 3 0 0 0. So, here it will be 0 5 and 0. So, in this case your this one is the pivot element. I have to make this one as 1. So, I am directly writing the rows 0 0 3 by 5 1 minus 1 by 5 0. Then it is 2 1 2 by 5 0 1 by 5 and 0. Next one is 6 0 34 by 5 0 minus 3 by 5 and 1. If you calculate the z j minus c j value, just we have done 0 minus 1 0 1 0. So, this is the entering vector, although still you have a for a corresponding to x 3 basic value is 0. If you calculate the ratio, then you will get 0 5 and 30 by 34. So, your outgoing vector is this one, therefore, a 2 is the this thing. And if you calculate, go to the next iteration, let us see what happens. Here from a 3, a 1 and a 5. So, a 3 will go out and a 2 will enter. So, here you will have a 2, a 1 and a 5. So, it is x 2, x 1 and x 5. So, it is 5 3 0 0 0. This is actually the routine now 3 5 0. So, it is 0 2 6. I am writing directly 0 1 5 by 3 minus 1/3 and 0. This is 2 1 0 minus 2 by 3 1 by 3 0. 6 already we have written 0 0 minus 34 by 5 5 by 3 and 1. So, again from here if you calculate z j minus c j 0 0 5 by 3 2 by 3 and 0. So, you see z j minus c j is greater than equals 0 for all j, and z j minus c j is greater than 0 for the non-basic variables. X 1 x 2 is in the basis, x 5 non-basic variables are a 3 a 4, corresponding to that z j minus c j value is greater than 0. So, although the problem is degenerate, but you are obtaining the optimal solution, unique optimal solution. X 1 equals 2, x 2 equals 0, z max equals 10. This is the optimal solution, but one thing should be noted. By this way, here when there was a tie, you may check it of your own. Instead of breaking the tie by our method, if you would have taken randomly anyone a 3 say, in that case you would have come back to the number of iterations would have been more, and you would have come back to the original solution. Now, just one thing, if you same problem if you see graphically, x 1 by 2, x 2 by 2 equals 1, x 1 by 2, x 2 by 5, this is equals 1, x 1 by 4 plus x 2 by 3 by 2, this is equals 1. This is the I am writing the constants. Actually, I want to just draw the curves. One curve will be something like this. There will be another curve that will be passing through this point and this point. It is no, this is wrong. One curve will be this one. There will be another curve which will be something like this, and the third one will be, it will be passed through this one. So, it will be something like this one. This is actually 5x1 plus 2x2 less than equals 10. If you see the feasible region is this one. Here this particular inequality constant is redundant over here, and if this was not there, then also the problem feasible region we have obtained. So, as I have told, degeneracy basically occurs due to the redundant one or more redundant constraints, which we have shown through this example also, that for this problem this particular inequality is redundant, it is not required, and the degeneracy occurred, and using our tie breaking rule we obtained the unique optimal solution for this. Thank you.